Okay, hello everyone and welcome to this very short but very informative video. When we are working with electromechanical conversion systems, one of the very important aspects that define the efficiency and the properties of these kind of devices, especially electrical machines, is related to the properties of the magnetic material. So today I have this very quick video that I will be calculating some of the most important parameters that you can find when you are defining the magnetic properties of any material. So if you remember from the theory, the BH curve is one of the most important characteristics that define the magnetic properties in the materials. So here there is a BH curve for the very specific case of a sample of silicon steel. The vertical axis represents what we call the flux density. In this case, we are using the letter B, and the units are represented by Teslas. And over here on the horizontal axis, you can see that we are representing what we call the magnetic field strength. We use the letter H for that physical quantity, and the units are amps per meter. So in this plot here in the BH plane, you can see that there are two plots, but in reality there is a single plot. There is a plot, and you can see over here that there is a 1000 multiplier, and that means that this plot represents the magnetic property between 0 and 6000. However, the second plot over here, the multiplier is 100. And that means that what we are representing over there is a sum out of the magnetizing curve BH. So you can see that the sum is going between 0 and 600. This very interesting sum over here is to make possible to represent and to see the magnetizing process when you are applying the magnetic field strength to the sample. So this curve is typically provided by the manufacturer, and in some cases we can get that in this way. And in this case, this is a graphical representation, it's a plot available for you. Or there are other cases that the manufacturer provide to you a table. In this example today, we are using the BH curve, the graphical representation, but in the future videos, we will be using the full numerical value. And there is a huge difference. Because when you are using this graphical representation, of course, you need to use graphical methods, and there are a lot of approximation in that case. So today, you need to be very careful because the approximation that you can get can give you a slightly different results. In this example, I am showing you how to use the graphical method, but the numerical results are coming from the real numerical analysis, the real numerical data provided by the manufacturer. So here there are 5 questions. The first one is to calculate the magnetization M when the magnetic field strength is 3500 ammeter. Then we have here another question, and it's again calculating M when the magnetic flux density is 1.3 Tesla. And then we have 3 questions over here related to relative permeability, absolute permeability, and of course the susceptibility. All of them when we have a H, in this case a magnetic field strength, of 1000 amp per meter. So without further delay, let's start the solution of this problem. The first thing that you must remember, as always, is the theory. You must remember that I already explained this equation over here. When we have a magnetic material involved in any magnetic configuration, we will have a strong influence on the magnetic flux density caused by that material. And in this case, we use the letter M to represent that very important property, and that letter M is basically the magnetization. So today, what we want to do is, if we know the B and H, if we know the flux density and the magnetic field strength, of course we can substitute the numerical values in this equation and we can obtain M. So here, in this case, for the first question, we know that the magnetic field strength is 3500 ampere meter. So what we need to do is basically calculating the value of the magnetic flux density. In this case, the numerical value will be 1.69 Teslas, but I will show you that I obtained that value using basically a graphic method. And the graphic method is very simple. You don't need to be scared about this. Is basically what we do is we go here and plot a straight line. In this case, 3.5 multiplied by 1000. That means 3500. So we intercept this red line, vertical red line. This is the input. We intercept with this plot over here, and then we plot a horizontal line, the second red line over here, the horizontal one, and the output is 1.69. Of course, I can see that many students can have the very different answer, but if we use the real numerical value of this curve, we will obtain the exact value, and in this case 1.69. So now it's just a basic exercise of numerical substitution in that equation. The magnetization will be B divided by mu 0 minus H. In this case is 1.69 Teslas divided by this very well-known constant 4 pi 10 exponent minus 7, and we reduce this 3500 ammeter. The numerical results, as you can see over here, is 1349 amps per meter. Again, one of the important things that you can realize is that when we are using magnetic materials, so the intensity of the magnetic field is, for the same intensity of magnetic field, we will get more flux. So right now what I will do is I will solve the second question, and the second question is extremely simple because we already know how to use the numerical method, the graphical method, and that is what we are using here. Now, for the second question, we know that B, and that is the flux density, is basically 1.3 Tesla. So what we need to do is use that as input, and in this case you can see 1.3 Teslas over here, the red horizontal line, and it's intercepting, in this case, the curve that is in multiplying by 100. Then we plot a vertical red line over here, and the output, as you can see, that is the magnetic field strength. And for this very specific case, you can see that the exact numerical value is 335 amps per meter. And again, calculating the magnetization is very simple because it's just a numerical substitution. You can see over here, M will be B divided by mu 0 minus H. And here you can see B, 1.3 Teslas minus 335 amps per meter. So from there, we obtain the numerical solution, and the numerical solution for this case, you can see over here, is 1034 point, in this case, this is a point, 17 amp per meter. So that is the magnetization that we can find when the flux density is 1.3. Now the next step is extremely simple because now my students, they are expert using the BH curve. So the next question, let me see over here. The next question is basically we want to know the permeability. In this case for 1000 amp per meter. So what we must remember is the relationship between B and H is defined by the absolute permeability, and the absolute permeability is the product between the permeability of the vacuum and the relative permeability. So the relative permeability will be basically calculated as B divided by H, where B is the magnetic flux density, H is the magnetic field strength. So now what I need to do is to obtain the magnetic flux density for an intensity of 1000 amps per meter. So we plot again the vertical line, we intercept with this plot over here, and we can see that in this case is 1.53 Teslas. From there is just basically an exercise of numerical substitution. And from there you can see that the relative permeability will be 1.53, that was calculated from the graphic method. 1000 amp per meter, that was the input. And we can see that the relative permeability in this case is 1218. There is no unit in the relative permeability. This is something that you must be aware. We don't have units when we are using the relative permeability. And one of the reasons is because the relative permeability is a number that when you multiply by the permeability of the vacuum, we obtain the absolute permeability. And in this problem, we has been asked about the value of the relative, the absolute permeability for 1000 amps per meter. So what we need to do is basically apply the equation, numerical substitution. From the previous question, we know that the relative permeability is 1218, and here we obtain the absolute permeability. Remember, the unit of the absolute permeability are in Henry per meter. Finally, the last question for this tutorial is basically calculate the susceptibility of this material. So, to be honest, to calculate the permeability of this material, to calculate the susceptibility of the material, we can use the relative permeability. And I remember that I introduced this question, this equation during classes. And from here, we can extract. It's very simple. You can see that the susceptibility will be the relative permeability minus 1. So it's very simple to see that extracting from that equation, I can obtain here the susceptibility. And that is basically 1218 minus 1, and you will get here the numerical value. In this case, this is the result, and again is without units. This is a relative number, and in this case, this is the susceptibility of the material. Well, thank you very much for watching this video, and I will see you at the next one. Bye now.